All right, this is protein part 3, and we need to address denaturing. So once a protein has achieved its mature tertiary or quaternary structure, it's ready to go. It's ready to be used as a building material, or maybe it's ready to undergo some chemical reactions because it's an enzyme. But that is all dependent on its shape, and protein can lose their shape. One way that protein can lose their shape is with heat, temperature. If you increase the temperature, what happens is you're adding more energy into that system. And the shape of this protein is largely the consequence of hydrogen bonding between the side chains and other polar interactions. So if you add energy, well, those hydrogen bonds, they're not the strongest bonds, so they end up wobbling and they break apart, and so the protein unfolds. Well, if the protein unfolds, it doesn't have its shape anymore. It can't do its job. If it's a structure, then that structure becomes unstable, and if it's if it's an enzyme, then it cannot promote the chemical reaction that it's attempting to assist. So it stops working. This is why we can't survive in extreme temperatures, because our proteins fall apart and we die. And this is also why we can't survive in extremely cold temperatures, because same thing, protein becomes denatured. And so that's what we are looking at here, is that this is our mature folded tertiary structure protein, and through some mechanism, maybe temperature, it unfolded. And the thing is that if your protein is undamaged, the energy wasn't enough to destroy a side chain or remove an amino acid or break the polypeptide. If it's undamaged, then when conditions return to normal, it will refold in its normal way. If it is damaged, it won't be able to do that. Now, another condition that can change or denature a protein is very acidic or very basic conditions. Now, if you are familiar with your general chemistry, you will know that their acidity is about the concentration of hydrogen ions. Well, hydrogen ions have a positive charge. So if you are flooding an area with a lot of hydrogen, if you're flooding it with a lot of hydrogen ions, a lot of positive charges, well, that's going to alter the polarity dynamics. Something that might, a region of that protein that might have bound to another region of the protein is now instead attracted to this hydrogen ion that's floating around out here. And it can interfere with the natural folding process of this. Same thing with very basic conditions. A lot of basic conditions involve hydrogen acceptors, which are often negatively charged. So again, you've got a polarity competitive issue, and the protein ends up being attracted to the molecules in the environment as opposed to the polar components of its own self. So acidity, basicness, and temperature are often components that denature proteins and stop them from functioning. Now let's talk about enzymes. We had that category of protein that conducts chemical reactions. Well, what do they do, and then how do they do it? That's what we need to address. So what do they do? Well, for chemical reactions to occur, the molecules have to contact each other, and they have to do so in the exact right way with enough force that their electrons end up trading or moving around or altering. For that to happen, there needs to be energy in the system. If there's absolutely no energy, everything is still, nothing is moving, then nothing will change. So you have to have energy to make a chemical change. And this is an idealized graph of what that energy means. You have the energy in the reactants. You have to add a little bit of energy. They have to have some kinetic energy. They have to have some collision. They've got to have some reason to change electrons. But once you've added that energy, they will then form their products, which has a lower energy state. You release this energy to the environment, and entropy has been satisfied. So you got to get up here. What enzymes do is they kind of make the process easier. They will take two different things and they'll mash them together. That means they'll take some of that energy responsibility themselves. So the molecules we don't have to push them as hard. Maybe they will alter the shape of the molecules ahead of time. So basically they lower the amount of energy needed to get them over the hump. So that's what enzymes do. They lower activation energy. How do they do that? Well, this is an idealized model. It's very simple. Because the enzyme, the protein, has a very specific shape, it can bind to its substrate. Substrate is the molecules that it is altering, and in binding to the substrate, it ends up changing its own shape as well as the shape of the molecules that it is bound to release new products. So you can see the new change in shape here, which pops these two products in half. So you can have proteins that take two molecules and put them together. You can take proteins that take one molecule and split it up. Lots of alterations. Enzymes are responsible for a lot of alterations. That's it. End of proteins. No more proteins. I hope this helps. Struggle well.